Okay, so in today's video, we're going to have a look at a few questions and examples from the last video, which was the beginning of differentiation, and that was called Differentiation Part 1. So if we start off with these two questions here, we have using the limit law theorem of differentiation. Remember, that's the one that says the derivative of x is equal to the derivative of f of x, sorry. Okay, so in today's video, we're going to have a look at a few examples from the last video that we did on differentiation. That was called Differentiation Part 1. And with these questions, we're asked to start off with, using the limit law theorem of differentiation, remember that that's the one that looks like this. So if we have some function of x, then the derivative, so the derivative of x is equal to the limit as h moves to 0 of f of x plus h minus f of x on top of h. Okay, so this is the formula that we're looking at using. We looked at that in the last video. This one here is important. And using this formula, we're asked to find the gradients of the following functions at their respective points. So we'll start off with question 1, which looks at f of x being equal to 4x squared, and we're trying to find the gradient of that function when x is equal to 3. And we're going to use the formula that we've highlighted in blue. So the gradient, or the derivative of x, is a better way of saying it. The derivative of x, in this case, is going to be the limit as h moves to 0 of f of x plus h. So we know that f of x is 4x squared. So f of x plus h is going to be 4 lots of x plus h squared, and we will take away f of x, which is 4x squared, divided by h. Okay, now that we have that there, we're going to come over here and simplify this down to try and get rid of the h's. Okay, so we'll start off with expanding out that x plus h squared bracket there. So we'll have the limit as h moves to 0 of 4 lots of, and this is going to be x squared plus 2hx plus h squared, expanding out that bracket, take away 4x squared on top of h. Okay, we can now put this 4 into all of those brackets, so the 4 into there, and into there, and into there. So we will get the limit as h moves towards 0, and we get 4x squared plus 8hx plus 4h squared, take away 4x squared, divided by h. And we can see now that these 4x squareds are actually going to cancel out. So this 4x squared will cancel with that 4x squared. And we are going to get left with the limit as h moves towards 0. And now I'm going to take a common factor of h out, remember, so that when we're dividing by the h here, we can cancel those h's out. So if we bring the h out, h outside of 8x plus 4h divided by h, these h's here can now cancel by bringing that common factor of h out, right? And we are left with, again, the limit as h moves to 0 of 8x plus 4h. And remember, as h is getting closer and closer and closer to 0, this 4h term becomes so small that it doesn't have an impact, right? And we're just left with 8x. So we know that if f of x is equal to 4x squared up here, then the derivative is going to be 8x. So what is the gradient of the function of f of x at the point when x is equal to 3? Well, we just put 3 into the derivative formula, right? So the derivative of f of x at the point 3, we can write like that, is going to be 8 lots of 3, which is going to be 24. So what we are saying is if we take this function here and graph f of x is equal to 4x squared, and we look at when x is equal to 3, we're going to have a gradient of 24 at that point. Okay, so that's the first one solved. The second one is going to be a similar process, but we've got a g of x. Okay, so we'll solve this one down here, and we will say that g the derivative of g of x is going to be the limit as h moves to 0. And don't panic that the f and the g don't match up in the formula, right? You know, g of x isn't the same as the f of x. We just change all the f's to g's because the f and the g are just labels of our functions, right? So the limit as h moves to 0 of g outside of x plus h, take away g of x on top of h. Right, so let's put some values in for g of x plus h. Well, we know g of x is 2x cubed. So g of x plus h is going to be 2 outside of x plus h cubed. And of course, g of x is the 2x cubed dividing by h here. Now we have to expand out these brackets where we're expanding a cubic. Okay, so how I like to do the cubic expansions is, if you have a cheat sheet for it, great. But if not, I like to do it this way. 2 outside of x plus h. I'll try and make a squared bracket because we can expand them easily. And then left over is going to be another x plus h like that, right? Take away 2x cubed divided by h. Now what we can do is we can expand out that square bracket. So again, the limit as h moves to 0 of 2 outside of, we get x squared plus 2hx plus h squared. Multiplying that by x plus h, taking away the original function, the 2x cubed, dividing by h. The writing becomes a little bit tedious, especially when we end up with cubics, right? Because we've got to write in the limit as h tends towards 0 and the divide by h bit. But if we continue through here, I'm now going to expand these two brackets. So I'll do them in red, that bracket and that bracket. So if we do that and we leave the 2 outside, we get we're going to do x to the x there, and then to the h, and then the 2hx to the x, and then to the h, and so on. So we end up with 2 outside of x cubed. Okay, x squared times x is x cubed. We then get plus hx squared plus 2hx squared plus 2h squared x plus h squared x plus h cubed, and take away 2x cubed divided by h. Okay, again, now we've got to expand that 2 out. Okay, the limit as h moves to 0, and we put the 2 through all of these terms. So 2x cubed plus 2 lots of hx squared plus 4 lots of hx squared plus 4 lots of h squared x plus 2 lots of h squared x plus 2 lots of h cubed, take away 2x cubed, and dividing all of that by h. We can now simplify some of the terms on this numerator. So again, the limit as h moves to 0. And you probably won't be asked to do a question with a cubic, but what it is good for is it's good for your algebra, right? So here we can see all the like terms. So if we take hx squared, we've got hx squared here, here, and that appears to be it. So we will group those together. 2x cubed, we have 2hx squared and 4hx squared, so we can get 6hx squared. And if we group the h squared x's, we have 4h squared x and 2h squared x. So we end up with 6h squared x. And then we have the 2h cubed left over, take away the 2x cubed. And there's another cancel out here, right? This 2x cubed and this minus 2x cubed, these two here, they're going to cancel as well. So we can get those out of it. Divide by h. And now we can bring out a common factor of h. Okay, to help get rid of that h on the denominator there. So the limit as h moves towards 0, we have a h outside of, we're going to end up with 6x squared and 6hx and 2h squared divided by h. These h's will cancel, and we will be left with just what's on in the brackets on the numerator there. We will end up with 6x squared plus 6hx plus 2h squared. And as h moves closer and closer and closer to 0, this term is going to become so small that it doesn't matter. And this term is going to become so small that it doesn't matter. Okay, remember if we do 6 times 0 times x, that's going to be 0. Of course, we're not quite getting there because we never get to 0. But 6 times 0.0001 times x is still going to be pretty small. So as we move as close to 0 as we can, these terms are going to cancel out. So we can get rid of those. They effectively become zeros, and we end up with 6x squared. So we know now that if g of x is 2x cubed, then the derivative is 6x squared. Okay, so we got those terms there. Now, what is the gradient going to be when x is equal to 2? Well, we take our derivative here, and we say that the derivative when x is equal to 2 is 6 lots of 2 squared, which is 6 times 4, which is 24. So your gradient is going to be 24. The same as the other question. It's funny how that worked out. Okay, now the next few examples, okay, are going to be using the shortcut trick that we learned. Okay, so we'll come over here and we will say we're going to try and find the gradient. Finding the gradient of the following functions at their respective points. Using the general formula for differentiation. Formula for differentiation. Okay? Now, remembering that this general formula was if f of x equals ax to the power of n, then the derivative is going to be n times ax to the power of n minus 1. That's our formula, and we got that in the last video by looking at our observations. Okay? Now, let's come up with a few examples. For number 1, we're going to say that f of x is equal to 4x to the 5, and we're going to find the gradient when x is equal to 1. Okay? So, what would the derivative of f of x be? Well, we know that from this formula, f of x being 4x to the 5, and we can use our formula to say that a, in this case, is going to be 4, and n is equal to 5. So what we do is we say that the derivative of f of x is going to be n times a, which is 4 times 5, so 20, 20x to the power of n minus 1. So 5 minus 1 is 4, 20x to the power of 4. And when x equals 1, the derivative, so the derivative at 1 is equal to 20 lots of 1 to the power of 4. 1 to the power of 4 is just 1. We end up with 20. Okay, that would be our answer. So the shortcut is so much easier than doing this this working out here. We saw that just with cubics, we had to do all of this work down this left-hand side, right? Imagine if we had an x to the 5. That would just go on forever. So it's good that we have this little shortcut method. Now, another one that we have to deal with is if we deal with when n isn't a nice positive integer, right? So in this case, it's 5. It's a nice positive integer, a round number. What if we end up with n being like a half, or, n being negative? So let's have a look at those. We'll do 2 more examples. So number 2, we're going to say that f of x is equal to x to the power, or the square root of x. Okay? I almost gave it away there. We can rewrite this as x to the power of a half. Right? Now, if you're not sure on that, you may need to go and revise how to transform square roots and stuff like that into this form, into this indice form. However, we can write this as x to the power of a half. And now we just follow the same process, right? Well, we know that a in this case, a is equal to 1. Okay, we could put an imaginary 1 out the front here. And we know that n is a half. And we know that So the derivative, using our formula in the blue there, okay, we know that the derivative of f of x is going to be n times a, so a half times 1, so a half times x to the power of minus a half. So a half minus 1 is going to be minus a half. Now, is there a nicer way we could write this? The answer is yes. We know that anything to the power of a negative indice is 1 over that to the positive indice, right? So if I do this over here, e.g. X to the power of minus n is equal to 1 over x to the n. So in this case, we're looking at this half here, right? So we can write this as a half times by 1 over x to the half. Okay, so we've moved that negative into a positive by putting it on the denominator. And we know that x to the power of half is the square root of x, a nicer way of writing it. So if we multiply these fractions together, we get 1 on top of 2 root x. 2 times the square root of x. And if I give you a value for x, so for example, when x is equal to 5, we can find the gradient when x is equal to 5 of the original function by putting it into this formula that we just came up with. The derivative at 5, or when x is 5, is 1 divided by 2 times the square root of 5. And that would be your answer. Okay? Now, a final one is when x is actually negative, and we'll have a look at that. So, if we do part 3, and we say f of x is 2 divided by x to the power of 3. Now, how are we going to get this into the form? We want it into the form of ax to the power of n, right? Remember, our formula works when f of x is ax to the power of n. So how can we get it into that form? Well, we know that we can rewrite this x to the cubed on the denominator as x to the minus 3 on the numerator. So 2x to the power of minus 3. And we saw that with this bit that I highlighted here. Right? We'll highlight that there. So that's important. That's how we've done that conversion. And now we can say that the derivative is going to be minus 3 times 2. So minus 6 times x to the power of minus 3 minus 1. So that's going to be minus 4. And now if we want to rewrite this with positive indices, we just put that x to the minus 4 on the bottom as x to the 4. So we say it's minus 6 over x to the power of 4. And that would be your solution for the derivative. And again, if I was to ask, say, at the point when x is 2, so the gradient of f of x when x is 2, well, the gradient when x is 2 is minus 6 over 2 to the power of 4. So we've got 2 times 2 is 4, times 2 is 8, times 2 is 16. So minus 6 over 16, and we can simplify that down. Dividing by 2's, we can say that's minus 3 over 8. So that's it for today's video. There's a few examples there. Ways to do it using the limit law theorem, and then ways to do it using our shortcut theorem. And the shortcut, or the general formula, is going to be far more useful and far more important as we move further on. Okay. Thank you very much.